Thank you. This is John working with Yoram, my fabulous colleague from the Technion. And since we're going to talk about common knowledge, let's remove this. Sorry? Control Shift Alt H. You're a wizard. Okay. So let me give you an informal definition. The formal definition will come in a few slides. Many of you know this. When we say that players have common knowledge of some fact phi, means that all players know phi. All players know that all players know that phi holds. All players know that all players know, et cetera, for any level of nesting. And, you know, as I said, we'll see a formal definition soon. This was just to create kind of common knowledge of an informal definition. The problem is that this actually did not create common knowledge, even of the informal definition. This is called the Halpern-Moses paradox. Goes back to the 80s. It's been called the Halpern-Moses problem by Arrow, Aumann, and Kurtz, and a paradox by Stephen Morris. We're going to call it the Halpern-Moses paradox. And it goes like this. So these are my two kids, Shachak and Eshid. There's no common clock. And assume that at some point the sender, Eshid, wants to send a message to the receiver, and assume that the message is guaranteed to arrive at either 1 or 2 seconds. Say that it arrives at time t+1. So at t+1, the sender still does not know that the message has arrived because the sender considers it plausible that the message arrived at t+2. So only at time t+2, the sender knows that the message has arrived, but at t+2, the sender considers it plausible that the receiver considers it plausible that the message was sent at t+1, at which case the sender would not know that it arrived. So only at t+3, the sender knows that the receiver knows that the sender knows that it had arrived, but not before. And similarly, I'm not going to draw more drawings like this here. Only at t+4, the sender knows that the receiver knows this. And every second that elapses, there's another sender knows that the receiver knows added to the stack. But at no finite time are these true for any arbitrary level of nesting. So actually common knowledge of the fact that the message was sent is never attained here, not even at time, million seconds or whatever. And in particular, the content of the message never becomes common knowledge. And to make this even more stark, if you add back and forth messages, play with it, whatever you want to do, it's not going to help. So whoever here is familiar with a beautiful paper of Giannakopoulos and Polymarchakis that shows that if you send the priors back and forth sufficiently many times, there's common knowledge of priors. That breaks if you introduce even the slight timing friction. So there are quite a lot of implications to this. Common knowledge assumptions are abundant in economic theory and game theory. Let me quote Bob Wilson by saying that game theory has a great advantage in explicitly analyzing consequences of trading rules that presumably really are common knowledge. It is deficient to the extent that it assumes other features to be common knowledge. But, even the part that Bob takes for granted, which is that trading rules are common knowledge, if you do this kind of analysis with timing frictions, if I'm talking to all of you on Zoom and I'm saying, here are the rules of the game we're all going to play now, here are the rules of the mechanism, and if there's even a slight, fraction of a second timing uncertainty on Zoom, there will never be common knowledge of the rules of the game, of the rules of the mechanism. And all of the papers that deal with how people play on auctions assume common knowledge of these rules. So, and on the other hand, common knowledge seems to effectively arise in the sense that virtually all of the standard consequences of common knowledge hold. This is in contrast with the email game, for example, where theoretical consequences of common knowledge theoretically break. And today I'm going to show you a new definition for common knowledge. It coincides with the traditional one in static settings, but it relaxes it in dynamic settings, and it's general enough to arise in many settings of interest, including those of the Halpern-Moses paradox. And on the other hand, it's strong enough to imply your favorite static consequence of common knowledge. It's not going to be I knows that J knows that I knows that phi. It's going to be for our example earlier with my two kids, it's going to be I sends the message, and as he does, he knows that J at some point will receive. He doesn't know when, but he knows that when J will receive, J will know. J will J will receive, and when he receives, he will know that I sometimes sent it, that when he sent J, he knew that J will receive, and that phi. Sorry, this is, yeah, good. There's a lot of literature on common knowledge. I'm gonna skip this if it's okay. Model. So we're mostly gonna follow the notation of Gonczarowski 94. That's the chapter in the Handbook of Game Theory. We're gonna have a finite set of players. Time is gonna be the natural number starting with 0. We're gonna have an abstract set of histories. You can think about each small omega history as uniquely identifying, for example, all of the actions played, all of their consequences, all of their, probabilistic consequences, all of the things that were done and could only have been done because of these consequences, et cetera, et cetera. And the set of history time pairs is denoted omega bar. So omega comma t, which is a single point, we're going to call it a point in omega bar, is a single history at a single time, a specific history at a specific time. And each player is going to have a knowledge partition over omega bar. So for example, if omega t and omega prime t are in the same partition cell of the knowledge partition, it means that they are indistinguishable to I. If I is at omega t, I consider it plausible that it's actually omega prime t prime. And knowledge can evolve over time. That's the point of having the partition over omega bar rather than omega. And a major departure from the literature, we do not assume common knowledge of a global or absolute time, meaning that omega t and omega prime t prime could be indistinguishable to I, even if t does not equal t prime. An event is any subset phi of omega prime. For now, don't worry about measurability. For example, the event it trains is all of the points, so all of the sets of, history, comma, time, such that at this history, at this time, it rained. And for every player I, for every phi, we define I knows phi as the set of all points such that their entire partition cell contains phi. So not only that point is in phi, but every point that is indistinguishable to I from that point, also the event phi holds in it. And ki phi is an event, so you can say j, ki phi, and all of these stuff. Ki phi always implies phi. I knows phi, phi is true. If it is actually an equality, meaning that whenever phi holds ki knows this, then we say that phi is I local. For example, I'm raising my hand is a Yannai local event, and I'm, James is I received from James that he showed me 5 minutes remaining, not yet though, is also a local event to me receiving. So for a set of players I and phi, we'll define everyone knows phi as everyone knows phi. And the traditional definition of common knowledge, as we said, is everyone knows phi, everyone knows that everyone knows, et cetera, ad infinitum. This is, again, an event. And this is an event that is I local for every agent, same event. So when this event arises, everyone simultaneously suddenly knows this. They didn't a minute before, but they do now. And this is the heart of the Helper-Moses paradox. It leads to many impossibilities because it says that with even minor timing frictions that prevent things from arising simultaneously at the minds of everyone, no new common knowledge can ever be formed. We have a theorem and examples, whatever, in the paper. So what do? So this is a paradox. When you have a paradox in set theory, what do? You give a better definition for a set, or you give a different definition for a set. We're going to give a different definition for common knowledge. So fix an event phi. For a player I and an I local event psi I, so for example, I is sending a message or I is receiving a message, we're going to define I at event psi I knows phi as the following. So it at some point in this history, psi I holds. So at some point in this history, I sends the message. And in addition, whenever psi holds in this history, I knows phi. So this is I at psi, whenever that event holds, knows phi. And for a set of players, we're going to say that a tuple of events is an I profile if it's a tuple of local events, one for each agent. For example, I'm sending and James is receiving is a Yannai James tuple. And for a set of players and an I profile, we're going to define everyone in I, each of them at the event assigned to them by this tuple knows phi if exactly what I just said. And we're going to define common knowledge or dynamic common knowledge, if you wish, among these players at these events of the fact phi as everyone, each at their own event knows phi, everyone, each at their own event knows the fact I just said, everyone, each at their own event knows the fact that I just said, etc., etc. That sort of thing. A few notes are in order. As I defined this psi I at psi phi, it is technically a time invariant event. If it holds at a specific point in a run, it holds throughout the run. And this event, it's for technical reasons that we're going to see in a moment. This event by itself does not imply phi because it holds throughout the entire run. Rather, it implies that for every I, when psi I hold at some point in that run, maybe not at that time, maybe at some other time. And whenever it does, phi then holds, and I then know that phi holds, and I then knows that whenever psi j holds, phi then holds as well, and j then also knows that phi holds as well, etc., etc. So for each I, the relevant non-time invariant event is actually C superscript I, all that stuff from before, which we defined to be psi I intersection this time invariant event. And the fact that these are different events for different agents is exactly what enables symmetry and non-simultaneity. And this event, this, I special event does imply phi and is local to I. And note that again, this is no longer one event that's local to all of the I's, which is what gave rise to the Halpern-Moses paradox. This is a different local event for every I, but they're all kind of defined from this global event that helps us define stuff and solve stuff. So back to the message sending with unknown delay example we started with. So let psi alpha be the alpha local event. A message with content C is sent from alpha to beta. Let beta be the beta local, psi beta, sorry, be the beta local event. A message with content C is received by beta from alpha. And assume furthermore that the content C contains evidence that some fact phi is true. So formally it means if such a message was sent, then phi holds for some time invariant event phi. So then we can prove, this follows from basic general lemmas that we prove, that whenever such a message is sent, it is the case that it is common knowledge between the sender alpha as he sends the message and beta as he receives the message, that phi. Or in English, in all histories in which alpha sends to beta a guaranteed to arrive message with evidence of phi, it is common knowledge between alpha as he sends and beta as the message arrives, that phi. So this arises in this setting, in many other settings. You can say it circumvents the Halpern-Moses paradox because it arises, even with such timing frictions. In the paper, we have general tools and theorems to show emergence in many other settings, reachability and whatnot. We have analogs for all of these. But you could tell me, so it arises, so what? What can you use it to prove? The true event always arises. You can't prove anything from it, almost anything. So as we said, many foundational mechanisms and game theory results rely on common knowledge assumptions. For example, there's a beautiful paper by Brandenburg and Deckel who show that in a static context, common knowledge of rationality and of the rules of the game implies rationalizability of the solution concept. A lot of the literature has focused on relaxing the common knowledge of rationality portion of this statement. But as we said, the common knowledge of the rules of the game statement is also sometimes problematic if you have timing frictions. And what we show in the paper is that virtually every static theorem involving common knowledge that including the one by Brandenburger and Deckel, including many others, can be generalized to a dynamic setting via principled across-the-board arguments. I'm going to show you today this kind of what does it mean to translate with respect to Aumann's agreement theorem. And I'm going to do this for 4 reasons. First of all, it's a beautiful fundamental result. Second, adapting the probabilistic statement of this result is actually less straightforward than non-probabilistic results like Brandenburger-Deckel. 3, it's known to not be implied by any finite level of nested knowledge. So you see that what I defined is actually not implied by simpler building blocks. And for, it's already canonical that this is important in dynamic settings because of Yannai so that you see that I'm not cherry picking results. So let the two players be alpha and beta. Endow omega with some probability measures. Some histories are more likely than others. You can write Aumann's agreement theorem as following. Let phi be a measurable event. If for some q alpha and q beta, we have that at some point, at some run, it is common knowledge instantaneously at that moment that alpha's posterior for phi is q alpha and that beta's posterior for phi is q beta, then q alpha equals q beta. This is Aumann's agreement theorem, beautiful theorem. It requires this traditional kind of common knowledge that we know that doesn't arise with timing frictions. So here's our version of the agreement theorem for dynamic common knowledge. So the blue, all of the differences are in blue. Let phi be a measurable time invariant event. Why time invariant? Because if we're thinking about my posterior for the event as I'm sending a message and James's posterior for the event when he receives a message, obviously his posterior might be it's not raining and mine might be it's raining if it's raining when I'm sending and not when he's receiving. So I'm talking about a fact that's fixed over time. If for some q alpha and q beta and for whichever I profile of local events, singular events, each of them occurring once throughout a run, this is needed for the probabilities to make sense. We have that it is common knowledge that that psi alpha, me sending the message, for example, hold at some point in the history, and at that point, my posterior for phi is q alpha. And psi beta holds at some point throughout, James receiving throughout the history, and at that point, James's posterior is q beta, then q alpha equals q beta. So, and if you couple this with our machinery to show that it emerges, together they recoup Giannakopoulos and Polemarchakis' result, even with time limitations. Let me almost finish by telling you that we can also use this, in a more of an economic setting to characterize equilibria in dynamic Bayesian coordination games. So coordinated attack games is our name for a family of two-player dynamic Bayesian coordination games, no common clock again. There's a Bayesian prior about the clock lags, about message delivery delays, and also about learning when and how each agent learns the state of nature. So each such prior would define its own coordinated attack game. Each player may decide whether and when to initiate an attack. Players are better off initiating attacks if the state of nature favors an attack. That's what I meant when I said learning the state of nature, learning whether it's favorable to an attack, and with both players attack, and when each player attacks sufficiently early. Then both of them get positive utility. If a player initiates an attack, but the other does not do so early enough or at all, or the state of nature does not favor an attack, then both players suffer a loss. And initiating an attack early carries risk, but also has the potential for reward. That's the usual tension in such cases. And turns out that depending on the specific technology by which the players learn about the state of nature and communicate as captured by the prior, if our prior is messages arrive really fast or really slow, or we learn about the state of nature with this probability or that probability, this different technology, we get very, very disparate equilibria. We have examples in the paper for equilibria that coordinate attack using games in which the equilibria coordinate attacks using different numbers of the messages, different patterns of messages. It's a zoo. Nonetheless, we give a characterization of equilibrium behavior in every coordinated attack game, and this holds regardless of the specific learning and communication technology because we phrase it using knowledge. So this is the penultimate slide. So assume for simplicity that the utility from an unsuccessful attack is minus infinity. Otherwise, you need to take P common belief and modify it similarly between me at some event and you at some event, et cetera, et cetera. The theorem says in every coordinated attack game, there exists an Nash equilibrium with strictly positive welfare, if and only if there exists some I profile, such that with respect to the knowledge partition induced by I'm sending to James at any time everything that I know, and James sends to me everything that he knows, it is the case that common knowledge arises, at least at some run, that the state of nature favors an attack and everyone are in their event in this I profile early enough. We also have a theorem that says that we define a strategy profile using common knowledge, and we say that this is the welfare maximizing Nash equilibrium. And every coordinated attack game never results in an unsuccessful attack. Pareto dominates every other strategy profile that has this property. So, really quite an elaborate characterization. Discussion. This is actually one of the oldest questions at the interface of econ at CS. It wasn't covered in the 80s during a push to apply epistemic analysis to distributed computing. In our paper, this kind of comes full circle back into economic theory. We have better understanding of the concept of CS. It's actually, we've uncoupled that from simultaneity, if you wish. New definitions make common knowledge assumption at the heart of game theory hold in many more settings with many more kinds of frictions. It's a conservative extension in the sense that it's a relaxation only of the dynamic settings. It does overcome timing frictions. It does not hold with probabilistically successful deliveries like Rubinstein. There, what you need is common p-belief, but you might also need to modify it the way that we do to get characterizations. And many people here I know are thinking about blockchains and cryptocurrencies. Announcements of rules, for example, of smart contracts there are very, very asynchronous. Future work might want to use our notion as a building block in the economic analysis of such systems. Sorry for being a minute over. Thank you.